Okay, so welcome back to this next video in which we are discussing the class equation. Okay, so we've now discussed conjugacy classes, and what we're now ready to discuss is the actual class equation. So I'll just write our big title. So we're now going to actually discuss the class equation. Now the class equation applies for finite groups, and basically it is an equation that involves the order of the group, okay, which is why we need to be working with finite groups, so groups that have only a finite number of elements in a finite order. Okay, and basically what the class equation is going to do is it's literally just going to say that the order of the group is the same as the order of all of the conjugacy classes added together. Okay, so I want to draw back my picture of the group partitioned up into the conjugacy classes, and I want to add on one little thing that I didn't really stress in the previous video. Okay, so here is my group, capital G, and then once again I'll colour it in, and this time I'll have it in red here. Okay, so what we've now discussed is that we can indeed partition our group up into conjugacy classes, and that this is a well-defined partition of the group capital G. Okay, the thing I really want to stress now in this next picture of the partition of the group into the conjugacy classes is the centre of the group. Okay, so let me just mark on here the centre of the group. Okay, so let's say that this box here, this subset of my group, is the centre of the group. Okay, now of course if we're working in an abelian group, then the centre of the group will be the entire group, but let's assume that we're working in a non-abelian group for this picture, and therefore the centre of the group is a proper subgroup of the group. Okay, so here is the centre of the group. Now, the elements in the centre of the group, we discussed that the conjugacy classes that they will be contained within will be conjugacy classes that only contain one element. Okay, and that's why I want to mark this on now. So remember, the conjugacy classes of this portion of the group are going to be very small, so I'll draw them very small. So these are meant to represent conjugacy classes that contain only one element. All of the elements of the centre of the group are in a conjugacy class by themselves, basically, which contains just one element, and that's themselves, basically. Okay, so here are all the conjugacy classes of the elements that are in the centre of the group. Now the elements outside of the centre of the group, and as I say, if we're working in an abelian group, then there will be no elements outside of the centre of the group, and the partition of the group into conjugacy classes will be very, very boring, and it will just be partitioning up into these sets, which are sets containing one element, and you'll do that for every single element in the group. Now it will form a partition, but it's the absolute partition. It's partitioning every single element of the group apart. Okay, but if we're working in the non-abelian group, then the centre of the group won't cover the entire group, and therefore there will be elements of the group that are outside of the centre of the group, and they will be in more interesting conjugacy classes than the elements of the centre of the group. Okay, so I'll mark these on now. Okay, and remember, the conjugacy classes don't have to be the same size, just as the orbits of a group action don't have to be the same size, and to stress that I might put some more interesting ones here. So let's say these are all of these conjugacy classes. Okay, now if we're working in a finite group, then you'll have a finite number of conjugacy classes outside of the centre of the group. Okay, now what I want to do then is I want to mark on representatives of each of the conjugacy classes. So I'm going to have some little g1 within this conjugacy class, I'll have some little g2 in this conjugacy class, and this is literally just so that I can name the conjugacy classes. We'll have some little g3 in there, and more arbitrarily, of course in this case I've just got 7 conjugacy classes here, but more arbitrarily it will be g1, g2, G3, all the way up to the rth conjugacy class, GR, where R is some finite natural number. Okay, and that's the final conjugacy class outside of the centre of the group. Okay, so these are just representatives from each one of the conjugacy classes outside of the centre of the group, and therefore I can name up the conjugacy classes. I can name this conjugacy class here the conjugacy class dedicated to G1. Okay, I can name this conjugacy class here the conjugacy class of G2, and I'll put some commas in, then we'll have the conjugacy class of G3, and we'll go all the way up to the conjugacy class of GR, and these are all the conjugacy classes that contain more than just one element. So the conjugacy classes of elements that are outside of the centre of the group. Okay, right, so in this case, as I say, there will just be 7 conjugacy classes, so we go up to G7 in this case. So I'll just put them on for the completion of this picture. So here is G4, here is G5, and here is G6. Okay, so R would be 7 in this case, but more generally it will be going up to GR. And basically, this is what the class equation says. The class equation says that the order of the group, okay, so the number of elements in the group, is equal to the number of elements in all of these conjugacy classes. Okay, so firstly we're going to take the number of elements in the centre of the group. Okay, so we'll add on the number of elements in the centre of the group. So we're not going to go through all of the conjugacy classes of the centre of the group individually. They just contain a single element each, so they all have order 1. So the order of all of them together is just the number of them, which is the order of the centre of the group, basically. So we're handling this portion just with taking the order of the centre of the group. And then the rest of this, we need to add on the orders of all of the non-trivial conjugacy classes. So we need to have plus the sum from I is equal to 1 to R of the order of the conjugacy class GI, basically. So we go through all of these conjugacy classes from 1 to R, and we take that order and we add them on to the order of the centre of the group, and of course we will then end up with the order of the entire group. Okay, so really the class equation is just capturing the fact that this forms a partition that completely covers the entire group. Okay, so that is the class equation. However, it's usually written in a slightly fancier form, and the reason that we can write it in a slightly fancier form is that we can apply the orbit stabilizer theorem on these. But just before we do that, let me just say that if the group is an abelian group, then of course there won't be any conjugacy classes outside of the centre of the group. Okay, so you'll have none of this portion. This portion will go, and you'll just then have that the order of the group is the order of the centre of the group, and that of course makes sense because the centre of the group is the entire group in the case that the group is abelian. Okay, but in a non-abelian group you'll have this term appearing as well. Okay, right. So now what I want to do then is write this in a different form using the fact that these are all orbits. So now what we are going to remember is the fact that the conjugacy class of this element GI is in fact the same as the orbit of this element GI under this group action of the group on itself by conjugation. Okay, so we're going back to remembering that we had this group action and that the conjugacy classes were just the orbits of the elements in this group capital G under that group action, basically. Okay, right, and now we can use the orbit stabilizer theorem, which we proved in a previous video in this playlist on group theory, which applies for an arbitrary group action by a group capital G on a set capital A. And the orbit stabilizer theorem says, I'll remind you, that the order of the orbit of an element little a, and of course this relies on everything being finite, the order of the orbit needs to be finite in this case. Okay, so the number of elements in the orbit of an element little a is actually the same as the index of the stabilizer of A in G in the group G. Okay, and remember this means the number of left cosets of the stabilizer of A in G in the group capital G. Okay, so really what the orbit stabilizer theorem tells us about is a correspondence between the elements of the orbit of A and the left cosets of the stabilizer of A and G. Now let me just remind you of the definition of the stabilizer of A and G. So the stabilizer of A and G is all elements of the group capital G which when they act on the element little a, fix it. Okay, so it is a subgroup of the group capital G, and it's the subgroup of elements which, when they act on the element little a in the set capital A, fix it and send it onto itself. Okay, so this is the definition of the stabilizer of A and G, and if you want more about those, view my video on orbit stabilizer theorem. Okay, so what we're now going to do is then just think about what would be the stabilizer of an element of the group GI, basically. Okay, so we can now apply the orbit stabilizer theorem here and say that the order of the orbit of an element GI is going to be the same as the index of the stabilizer of that element GI in the group capital G. Okay, in G, of course. Okay, so now let's think about what the stabilizer of an element little gi in the group capital G would actually be equal to. So let's actually think about this. So we've got some elements of the group here. So remember, I know this looks terribly complicated because it's got the other index there, but remember this is just an element of the group. So forget the index there. Don't worry about the index there. Gi is just an element of the group. The I refers to this, but it doesn't matter as far as this orbit stabilizer theorem is concerned. So Gi is just some element of the group. Okay, it's just taking the place of little a here. Okay, and of course remember that our group action is the group acting on itself, so elements of the group are taking the place of little a. Okay, right, so the stabilizer of an element, little gi, in the group capital G, this is going to be the subgroup, and we prove in the video on orbit stabilizer theorem that stabilizers are always subgroups. Okay, so it's the subgroup that contains all the elements of the group, all little g is an element of the group, such that little g acting on little a, okay, and in this case little a is gi, and maybe I'll change this to g bar to stop us getting confused. So little g bar needs to act on little gi to give little gi back again. Now of course acting means conjugating in this case, so we need to be able to conjugate little gi by g bar to get little gi back again. Okay, so the stabilizer of little gi in the group capital G means all the elements of the group capital G, which when you conjugate little gi by them, actually have no effect on it. They send it back to little gi. Now, we have seen this definition before. In the previous video in the playlist on group theory entitled Centralizers and Normalizers, we have seen this definition. This is exactly what we would have called the centralizer of the element little gi in the group capital G. Okay, so remember, the centralizer of an element of the group capital G in the group capital G is defined to be the subset of elements of the group which, if you use them to conjugate the element little gi, do absolutely nothing to it. They fix it, they send it onto itself. Okay, so in fact, in this case, for this group action of the group on itself by conjugation, the stabilizers of elements of the group are exactly equal to the centralizers of those elements in the group. Okay, so we can now replace the stabilizer of gi in the group G with the centralizer of gi in the group G. So we're going to do that here, and then we're going to substitute in this index of the centralizer of gi in the group G for the order of the conjugacy class of gi. Okay, so let me get one final piece of paper to write out the final form of the class equation, the form of the class equation that you'll usually find it presented in. Okay, so the order of the group, and of course I'll remind you that we need a finite group. I didn't actually write that anywhere. I'll just bring this down. Finite group. This is very, very important. It only obviously works for a finite group. You can't apply this to infinite groups. Okay, right. So the order of the group here is equal to the order of the centre of the group, so that bit's very easy, plus the sum from I is equal to 1 to R of the index of the centralizer of gi in the group G in the group G. So G colon CG GI. Okay, and that's the form that people usually quote the class equation in. Okay, and I hope you understand where this actually comes from. So remember, I'll just remind you, these little GIs, these are representatives, and you can pick whatever representatives you like from the are conjugacy classes that are outside of the centre of the group. So you pick representatives from these conjugacy classes outside of the centre of the group, okay, and use them in this equation. So that's where the little gi comes from. Okay, and with that I will end this video in which we are discussing the class equation.